students. So in the last class we have learned about logic gates and universal logic gates. So what are logic gates? Actually, computers need a way to manipulate those ones and zeros so that they can do more complicated operations. Computers use logic gates to transform the ones and zeros from input wires. A logic gate accepts inputs and then outputs a result based on their state. So, logic gates or logic circuits include such devices as multiplexers, registers, arithmetic logic units, and computer memory, all the way up through complete microprocessors, which may contain more than 100 million gates. In modern practice, most gates are made from metal oxide semiconductors or field effect transistors. Compound logic gates, that is AND or invert or AND invert, that are more often employed in circuit design because their construction using the metal oxide semiconductor and field effect transistors is simpler and more efficient than the sum of the individual gates. So in this session we are going to learn about multiplexers. So what is a multiplexer? Multiplexer, shortly called as MUX, is a device allowing one or more low speed analog or digital input signals to be selected. It allows one or more low speed analog or digital input signals to be selected, combined and transmitted at a higher speed on a single shared medium. Multiplexer, the word itself means that many into one. Many inputs into one output. So multiplexer means many into one. It allows one or more low speed analog or digital input signals to be selected, combined and transmitted at a higher speed on a single shared medium. A multiplexer is a circuit used to select and route any one of the several input signals to a single output. A very simple example of an non-electronic circuit of a multiplexer is a single port multi-position switch. And multiplexers can handle two types of data: analog and digital data. So multiplexer is a combinational circuit that has a minimum of 2 raised to n data inputs, n selection lines and single output line. One of these data lines or data inputs will be connected to the output based on the values of selection lines. Since there are n selection lines, there will be 2 raised to n possible combinations of zeros and 1. So each combination will select only one data input. As I said earlier, it is also shortly it is called as MUX, MUX. So first we shall learn about 4 into 1 multiplexer, that is also called as 4 cross 1 multiplexer. In a 4 cross 1 multiplexer, there are totally 4 input lines ranging from I0 to I3, I0, I1, I2 and I3. These are all the input lines given to a multiplexer. And with this 4 input lines, the multiplexer converts just one output from this input lines. The output of the multiplexer here is Y, and for this it uses two selection lines, S1 and S0. S0 and S1 are the two selection lines used for a 4 into 1 multiplexer. For a 4 into 1 multiplexer, we know n equal to 4. N equal to 4 means that is equal to 2 square. Here m equal to log base 2 the power n. M equal to log 2 to the power 2 square, that is equal to 4. Here we may have 4 input lines. For a 4 into 1 multiplexer, we need 4 input lines, but only 2 selection lines, S0 and S1 are the selection lines. So the input lines for this multiplexer are I0, I1, I2 and I3, and the two selection lines are S1 and S0. The output given by the multiplexer is Y. Now to obtain Y, one of these 4 inputs will be connected to the output based on the combination of inputs present at these two selection lines. So from the truth table, it is clear that when the value of S1 and S0 both are 0, the output Y will be I0. So when the value of selection lines S0 and S1 both are 0, the output will be I0. The input line I0 will be routed to Y. And when S1 is 0 and S0 is 1, I1 will be the output. The input I1 will be routed to Y. When S1 is 1 and S0 is 0, I2 will be routed to Y. And when both S1 and S0 are 1, then the output Y is I3. So this is the truth table of a 4 into 1 multiplexer. That means it has 4 input lines, so 2 selection lines, and based upon the values of the selection lines, the input will be routed to Y. In any case, the output will be a single value, and based on the selection lines, values of the selection lines, the output will be displayed. The output will depend upon the values of the selection lines. When both S0 and S1 are 0, I0 will be routed to Y, and when S1 is 0 and S0 is 1, I1 will be routed to Y. When S1 is 1 and S0 is 0, I2 will be routed to Y, and when both S1 and S0 are 1, the output will be I3, that is I3 will be routed to Y. This is the functioning of a 4 into 1 multiplexer. Here, based upon the truth table for the 4 into 1 multiplexer, the Boolean function for output Y can be written as Y equal to S1 dash S0 dash I0. S1 dash means at first the value of S1 is 0. The value of S1 and S0 both are 0. So in the Boolean function we take it as S1 dash. We know S1 dash denotes the inversion of S1 and inversion of S0. That means both S1 and S0 are 0 at first. So to obtain the first value, to obtain the first Boolean function, we take the value of S1 as 0 and S0 and S1 both as 0. So in the Boolean function we can write Y equal to S1 dash S0 dash I0. This is taken from the truth table both S0 and S1 values are 0. So for denoting this 0 value, we put it as S0 dash and S1 dash. So S0 dash, S1 dash into I0, the output I0. So the first row of this truth table is taken as the function, Boolean function. So S1 dash plus S0 dash, S1 dash, S0 dash, I0 plus the next row, that is S1 dash. Here because S1, the value of S1 is here 0. So S1 dash S0 into I1 plus the next row, that is S1 S0 dash I2 plus the next row, that is S1 S0 I3. So the total of this will be the value of y, that is the output. So from the truth table, the Boolean function for this output could be written as y equal to S1 dash, that is the inversion of S1, that means S1 value is 0. S1 dash, S0 dash, S0 dash also denotes that the value here is 0. So S1 dash, S0 dash, I0, that is the first output. When both S1 and S0 have 0 values, I0, the input line I0 will be routed to y, that is the output will be I0. So this itself is written as y equal to S1 dash S0 dash I0 plus S1 dash S0 I1 plus S1 S0 dash I2 plus S1 S0 I3. The implementation of this Boolean function using AND and OR gates is given in the figure. That is, when S1 and S2, the values of at first S1 and S0 values are 0. We know from the truth table, at first the value of S1 and S0 both are 0. That means both S1 and S0 are inverted. The values are inverted. And then these two values are routed to an AND gate with the value I0. From the truth table, S1 at first, S1, S0, both S1 and S0 values are 0. That means the values of S1 and S0 are inverted so that it becomes 0, and then this is passed through an AND gate. AND gate, as you know, AND gate performs simple multiplication. That means we have to multiply the value of S1 dash and S0 dash with I0. That is our first Boolean function, the first part of the Boolean function. So both S0 and S1 are inverted, and this 0 value is passed on to the AND gate, the last AND gate, along with another input line I0. That is also, we get that I0 from the first Boolean, first part of the Boolean function, S1 dash S0 dash I0. Here it is ANDed, and then it is ORed to get the value y. You know, AND gate performs simple multiplication and OR gate performs OR function, that is our addition function. So this from the Boolean function, the first part of the Boolean function S1 dash S0 dash I0, that is ANDed, and then it is passed through a OR gate. And the second part, that is S1 dash S0 I1, that is performed using the second AND gate. The value of S1 dash, that is S1 is inverted, the inverted value of S1 and the value S0 along with I1 will be passed through an AND gate, and it is ORed to get the y value. In the same way, the third part of the Boolean function, that is S1 S0 dash I2, the value of S1 and the inverted value of S0 along with I2 will be ANDed, that is, it will be passed through an AND gate, and then it is out to get the value y. Similarly, the last part of the Boolean function, that is S1, S0, I3. Here both S1 and S0 has value 1, and both these without inversion, the values of S1 and S0 along with the value of I3 is passed through an AND gate, and then it is passed through an OR gate to get the output y. So this is the functioning of a 4-into-1 multiplexer. In the same way, we can get a 16-into-1 multiplexer, 16 cross 1 multiplexer, and the implementation of the 16 cross 1 multiplexer can be done using 8 cross 1 multiplexers and 2 cross 1 multiplexers. So 8 cross 1 multiplexer has 8 data inputs, as we have seen in the 4 cross 1 multiplexer. In a 4 cross 1 multiplexer, it contains 4 input lines and 2 selection lines. Here for a 16 cross 1 multiplexer, a 16 cross 1 multiplexer could be implemented using 8 cross 1 multiplexer and 2 cross 1 multiplexers. So for 8 cross 1 multiplexer, it contains 8 data inputs and 3 selection lines and 1 output. In case, the output will be 1. It could contain just 1 output. And 16 cross 1 multiplexer has 16 data inputs, 4 selection lines and 1 output. So two 8 cross 1 multiplexers are required in first stage in order to get the 16 data inputs. That means 16 cross 1 multiplexers are built with a combination of 8 cross 1 multiplexers. 2 8 cross 1 multiplexers are required for that. Since each 8 cross 1 multiplexer produces 1 output, we require a 2 cross 1 multiplexer in the second stage. So at the first stage, we use 2 8 cross 1 multiplexers, and at the second stage, we make use of a 2 cross 1 multiplexer by considering the outputs of the first stage as input and to produce the final output. So for implementing the 16 cross 1 multiplexer, we make use of 2 8 cross 1 multiplexers at the first stage, and taking the output of this 2 8 cross 1 multiplexers, we make use of 2 cross 1 multiplexer in the second stage to get the final output. So this can be implemented using 2 8 cross 1 multiplexers at the first stage, and the output of this 2 8 cross 1 multiplexers will be taken as an input for another 2 cross 1 multiplexer in the second stage to get our final output. So the truth table for this is given here. Similar to the 4 cross 1 multiplexer, at first both the values of S0, S1, S2, S3. So this contains 16 cross 1 multiplexer will contain 4 selection lines, and at first, that is the first row of the truth table contains all the selection lines. The value of all the selection lines will be 0, and when all the selection lines are 0, the output will be I0. The first input line, that is I0, will be routed to Y. And on the second row, S1, S2, S3 will be 0 and only S0 will be 1. In that case, I1, the input I1 will be routed to Y. This is a similar case, similar to 4 cross 1 multiplexer. And third, S2, S3 and S0 are 0, and S1, the value of S1 will be 1. In that case, the third input, that is I2 here. The third input here is I2. I2 will be routed to Y. And then S0, S1 will be 1 and S2, S3 will be 0. In that case, I3 will be the output. And next S3, S1 and S0 will be 0. Only S2 will be 1. In that case, I4 will be the output. Again, the values S3 and S1 will be 0 and S0 and S2 will be 1. In that case, I5 will be the output. And then S3 and S0 will be 0. Again, S1 and S2 would be 1. In that case, I6 would be the output. Similarly, on the next row, S0, S1, S2 will be 1. Only S3 will be 0. In that case, I7 will be the output. Similarly, we could complete all the rest of the rows in the truth table in a similar way. So from this truth table, we can derive the circuit using two 8 cross 1 multiplexer. As I said earlier, a 16 cross 1 multiplexer could be implemented using two 8 cross 1 multiplexers and one 2 cross 1 multiplexer at the second stage. At the first stage, here we make use of two 8 cross 1 multiplexers that contains 8 input lines. 8 cross 1 multiplexers contains 8 data input lines and 3 selection lines, S0, S1 and S2. One more input line is there for both 8 cross 1 multiplexer. So it contains 8 data input lines. Each 8 cross 1 multiplexer contains 8 input lines, data input lines and 3 selection lines. You know how did we get these 3 selection lines? For a 8 cross 1 multiplexer, n equal to 8. We take the value of n as 8. 8 equal to, or 8 can be considered as 2 raised to 3. Here n value is 8. 8 could be written as 2 raised to 3. So m value equal to log 2 log base 2 the power n. Log base 2 to the power 2 power 3 equal to 3. So we need 3 selection lines for a 8 cross 1 multiplexer. So in the same way, the second 8 cross 1 multiplexer is also designed here using 8 data input lines and 3 selection lines. That is the first stage of this circuit. And at the second stage, the output of these two 8 cross 1 multiplexer will be taken as input for the 2 cross 1 multiplexer at the second stage. So for a 2 cross 1 multiplexer, we make use of 2 inputs but only one selection line, that is we denote here it as S3. So the output of the two 8 cross 1 multiplexers will be taken as input for the 2 cross 1 multiplexer in the second stage, and the final output will be Y. Okay, I think it's clear now. So the same selection lines from the diagram, the same selection lines S2, S1 and S0 are applied to both 8 cross 1 multiplexers, and the data inputs of the upper 8 cross 1 multiplexer, the first 8 cross 1 multiplexer, are I8 to I15, and the data inputs of the lower 8 cross 1 multiplexer, that is I0 to I7. The first 8 cross 1 multiplexer, that is the upper 8 cross 1 multiplexer data lines, are I8 to I15, and the first data input, the input lines for the first 8 cross 1 multiplexers range from I0 to I8. These forms the input for the two 8 cross 1 multiplexers. Therefore, each 8 cross 1 multiplexer produces an output based on the values of selection lines S2, S1 and S0. From the truth table, we can give a Boolean function also. We can derive a Boolean function from the truth table itself. The outputs of the first stage 8 cross 1 multiplexers are applied as inputs for the 2 cross 1 multiplexer at the second stage, And here we make use of another selection line, that is S3. S0, S1 and S2 are the selection lines for the first two 8x1 multiplexers, and at the second stage for the 2x1 multiplexer we make use of selection line S3. If S3 is 0, then the output of the 2x1 multiplexer will be one of the 8 input from I7 to I0 based on the values of these selection lines S2, S1 and S0. If S3 is 1, then the output of 2x1 multiplexer will be one of the 8 inputs ranging from I8 to I15, and it is also based on the selection lines S2, S1 and S0. So the output from these 8x1 multiplexers will be taken as input for the 2x1 multiplexers, and for the 2x1 multiplexer we make use of only one selection line, and based on this selection line we can take either of the values, input values as the output Y. So I think you got the basic idea about the multiplexers. We shall continue on the next class. Thank you.